Okay, next important thing is input output curve. This is also known as input output behavior of the operational amplifier in open loop. So on the x-axis we have VD. Now VD means I have already told you that the difference between these two voltages, and output is, this one is the output, so V out and VD. So that is what we have plotted here. So as we increase VD, that is differential voltage has been increased slowly, output follows its increment. So you can see the behavior is very linear. As we increase the differential voltage, output increases linearly. But after a particular time, after a particular differential voltage, even if we increase the VD, there is no change in output voltage, and that particular limit is saturation voltage, and this output what we are getting stabilized is equal to VCC. What is VCC? Whatever is written here, Vs, that is supply voltage, and in transistor terminology we will use this or denote this as the collector voltage. So this is called VCC. So this VCC means power supply on the positive side. This negative VCC means power supply connected to pin number 4. So similarly, if we start moving or V negative start increasing from V positive, then the difference will be on the negative side, so it will move like this side. So in this condition again, after some time output will become stable or constant, and that will be equal to minus VCC. So if we talk about the amplification, this particular region is amplification region when we get a constant slope between VD and V out. Okay, so whenever OpAmp is operate as an amplifier, it should work in this particular range of VD only. So let's do one numerical calculation and see its importance. We know that its gain is 2 into 10 raised to power 6 usually, since this is in open loop condition, so its gain OL, open loop gain, is 2 into 10 raised to power 6. If gain is 2 into 10 raised to power 6, it means V out will be AOL into VD or V in, whatever you want to say, differential voltage. This is the formula. Now we already know this gain, that is 2 into 10 raised to power 6. So if our VD is, let's say, 1 microvolt, in that case the output will be, yes, 2 volt. Okay, but if we increase the VD, let's say it is 5 microvolt, when VD is 5 microvolt, in that case V out will be equal to 10 volt. Very good. Now we know usually we connect this operational amplifier at plus minus 15 volt, that is 7 number pin is plus 15 and 4th number pin is connected to minus 15 volt, or minus VCC is minus 15 and plus VCC is plus 15. So now we are increasing VD. At 1 microvolt we are having 2 volt, having 10 microvolt we have 10 volt. Since we know that the maximum output what we can get is 15 volt, so can you tell me, can you calculate what is the maximum VD, what is the value of VD when we are able to get 15 volt? What is the value of VD when we are able to get output as 15 volt? Let's keep the gain a constant, 2 into 10 raised to power 6. Yes, the VD should be 7.5 microvolt. So see the power of this operational amplifier. Even 7.5 microvolt signal can be converted into 15 volt. But sometime, in fact most of the time, it becomes a problem. Why is the problem? let's discuss another scenario. If the input voltage is 10 microvolt, theoretically output should be 20 volt, but it is not possible. I've already told you that the maximum output it can gives you is 15 volt. Yes. So if somebody asks you that gain is 2 into 10 raised to power 6 and you have given VD, that is differential voltage of, let's say, 1 millivolt, what is the output? So as per gain and VD formula, the output seems to be, I am saying seems to be, yes, 2000 volt, yes, 2 kilovolt, but it is not possible. The reason is, again, I have already told you that the maximum output what we can draw from the operational amplifier is the VCC, whatever is given to it. If we can design, yes, if we can design an operational amplifier which can operate on, let's say, 2000 volt on plus side and negative 2000 volt on minus VCC, yes, then it is possible to draw such high voltage at the output level. So please keep this thing in your mind that VCC decides what is the maximum voltage we can get after amplification. So I am again coming back to my previous question, that if we are not able to amplify a very small signal of 10 microvolt, why we are not able to amplify? Because output is constant, 15 volt. 10 microvolt output is 15 volt. 15 microvolt, 20 microvolt, 100 microvolt, 200 microvolt, 1 millivolt, whatever value more than this, you will always get 15 volt. So it means we have reached in saturation region. Okay, so we are not in amplification region. So to make this functionality in the practical scenario, when the difference voltage is not very small, sometimes it is millivolt, sometimes it is 100 microvolt, we need to do some modification in the open loop gain, and for that the scientists have proposed that this can be easily used in closed loop mode. So we will discuss later that how we can design or redesign the same IC. When it is in closed loop mode, its gain can be controlled. So closed, that is CL, can be redesigned as per your requirement, and that depends upon the additional circuitry that we connect outside this particular IC, that is R1, RF. We will use different resistors outside this OpAmp and we can design our own gain, but that will be definitely closed loop or feedback based operational amplifier. So that's all about input output curve. I hope you have understood its significance, that whenever we have to use in amplification region, that is where this green brackets have been shown, this is amplification region, then the VD should be very small, or we have to control the gain, because we know the maximum voltage what we can withdraw from this operational amplifier is 15 volts. So let's move ahead. These are some of the applications of operational amplifier. The most popular is definitely amplitude, that is amplification. Then we can use them as comparator, oscillators, filters, sensor. It should be sensor modules, because most of the sensors have very low output. So once we try to make those sensors directly compatible to devices or components like Arduino, Raspberry Pi, we use OpAmps within the sensor only, and those sensors are called smart sensors. And again, instrumentation amplifier for various measurement applications. This is the internal schematic. Don't worry, we are not going much detail into this circuit analysis, current or voltage measurement of this circuit, but this circuit has been shared with you so that you can understand what is inside the operational amplifier. So there are only discrete components of discrete components like transistors, resistors, capacitors. Okay, so that is why this is called analog IC, because inherently it contains transistors only. And if I tell you for 741 generalized version, there are 20 transistors. Those are being used within this circuit, and it has various stages. The first stage, if I tell you, is differential amplifier. Okay, where pin 1 and pin number 2 and pin number 3 has been compared. Next stage is current mirror, and the final stage is high gain amplifier. Okay, so you can also notice this is pin number 6. If I try to find out where are the pins, so this is output pins. Then other important pins are power supply pins, pin number 7 and 4, negative power supply. Then we have offset null, pin number 1, and similarly there is pin number 5. Yes, here it is. So here it is. You can see that the configuration is very symmetrical but opposite. So that is why we use back-to-back transistor when we are using offset null for 1 and 5. So one offset is being used for positive offsets, and another offset is to nullify the negative offsets. That is, when the input at pin number 2 and 3 is same and output is negative at pin number 6, then we use 5 number pin, and for positive offsets we use pin number 1. So these are the two inputs, pin number 2, pin number 3, non-inverting and inverting pins. So this is the internal schematic. This will help you to understand sometimes that why this is so, why we are saying internal compensation, why the internal behavior is like this. Because okay, the question again comes that if we have same voltage at pin number 2 and pin number 3, why there is difference or there is some output voltage? The reason is in this circuit. We can say, since there are many transistors connected in back-to-back or individual configurations, sometimes, or in fact many times, their internal parameters of these transistors of Q1, parameters of Q2 may not be similar. Okay, so that difference in their parameters give reason to give some offset voltage at pin number 6. Let's discuss some of the features or the properties we expect from an ideal operational amplifier. So we can note down, these are very important. Ideal operational amplifier must have infinite input impedance, zero output impedance. Why this is so? Input impedance should be infinite. What does it mean? It means whenever we connect operational amplifier to a sensor, it should not load the sensor. The reason is its input impedance is very high. It will not suck the current from its previous circuit. That is the meaning of high input impedance. And what is the meaning of zero output impedance? Just reverse to it. If we connect output of OpAmp, suppose this is an operational amplifier, if we connect this operational amplifier to another circuit, okay, its output impedance should be very low, because it should not load the next circuit. As we are expecting from this circuit that its previous circuit should not be loaded, so we keep its input impedance is very high. But when we are connecting with the next one, we don't want that this operational amplifier withdraw much current in this loop, so we make Z0 or output impedance very low. Okay. Another ideal characteristic is infinite open loop gain. Yes, we expect that gain should be very high, we can amplify signals like microvolts or something like that. Next is bandwidth should be infinite. We can operate at any frequency. That is the meaning of infinite bandwidth. That is, operational amplifier should be able to use from DC, that is 0 Hertz frequency, up to megahertz or even gigahertz. That is the meaning of infinite bandwidth. We will see practically all these things possible or not, but these are ideal characteristics. Then fifth one is zero noise contribution, that is it should not generate any noise. And the last one is zero DC offset output, that we have already told that it should not include any DC component in the signal when we are amplifying any signal. So let's see what are the practical output, practical characteristics of operational amplifier. So practically input impedance is in the range of 500 kilo ohm to 2 mega ohm. It is not infinite. Zero output impedance is definitely some impedance will be there. If we design a circuit, you can decrease it, but you cannot make it zero. If there is some component, it is consuming some current, voltage, it has to have some resistance. Okay, so it could be low, even lower than 20 ohm sometimes. Infinite open loop gain, yes, we can increase the gain up to 2 into 10 raised to power 6 or 5. Bandwidth is limited. Here it is mentioned few kilohertz, but today, these days, even we have operational amplifiers whose bandwidth is in megahertz. Noise contribution is there, but and the last one is we cannot make its offset to a zero level. So practically all the characteristics are not possible, but we always try to design some kind of circuits where we can move towards ideal characteristics. These are the references being used in this presentation. So in the next session we will discuss important parameters that just we have discussed, practical parameters in more detail. So thank you students, thanks for watching this video.